Good morning, students. What I'd like you to do is, obviously you're not going to send me a private chat here, but I want you to just pause the video and look at this graph and think about what do you know about it already. We're digging into your prior knowledge here. So press pause, think about everything you know about this graph, and then unpause it when you're ready. Okay, well, hopefully you remembered back to the fact that this was the graph of a quadratic function. And the graph had a special name. We called it a parabola. Anytime you have a U-shaped graph that's a parabola, it can open upwards or downwards. And then it even had a vertex and an axis of symmetry. So we're going to highlight those pieces just on this graph, just so you guys get a nice frame of reference of what we're talking about. When we talk about the vertex is the lowest or the highest point on the graph. In this case, this is my minimum value. It's the lowest y value. Excuse me, it's the lowest y value on the graph. Now, the axis of symmetry is the value of the x value of the vertex. So notice if I move over a certain x value and then I go down, that goes right through the vertex. So the axis of symmetry is this dotted line that's actually not part of the graph, but it's the vertical line that splits this parabola into two equal halves. Symmetry. So anything on the left side, now notice if I pick a point, let's pick this point because we're going to make reference to it in a little bit, but this point here looks to be about 1.5 units away from the axis of symmetry. And if I go the other direction, that is the same distance, 1.5. So the points that are located on the parabola are equidistant away from the axis of symmetry in the horizontal line. Right, so this point here, if I reflected it over, it would be the same distance away. And the nice thing is if you know one of those points, you can automatically reflect it over to get another point. So we have our parabola, axis of symmetry. I'm going to make a reference to one other thing that you may have noticed, and that's this point right here and this point right here. Let's use this specific example. These are the X-intercepts. And this one is at the spot -1, 0. And this X-intercept is at the spot over 1, 2, 2, 0. Well, let's think about that quick. If I have my X-intercepts, those are the spot where y is equal to 0. Well, if x is equal to a number and y is equal to 0, we also call those solutions, or we might call them zeros. And the reason why I bring that up is we just finished a unit on factoring and solving and the quadratic formula, so we were able to find solutions. Well, let's think about that. If x is equal to -1 and x is equal to 2, well, these solutions came from a factor. So what if I add 1 over to this side? So it's x plus 1. And what if I add, and so then it'd be equal to 0, and then I subtract 2 over to this side. And then since they're both equal to 0, we could set them each equal to their own 0. And notice this is starting to look like the factored form. Right? We have a binomial times a binomial. If I distributed all of this, the only thing that would make this different, it would give me the equation of the tangent line. The only thing that it would make it different is there's some multiplier of an a value here that we don't know until we use another point to try to find that. But I just wanted you to kind of take a look at this form right here. And this is called the intercept form. Maybe I'll put form there. Intercept form of the quadratic function. And that's one of the ways that we're going to look at graphing. Now notice where the value 1 came from and -2. They came from the solutions of x equals -1. So see how that's the opposite value? And then here, x minus 2, the opposite of -2 is +2. So the solutions are kind of present in the factored form of the quadratic, and that means we can automatically plot those down as points on the graph. Another thing to look at is let's think about the value of this axis of symmetry. If the solution is at -1 and the other solution is at +2, then this distance between the axis of symmetry and the left 0 and the axis of symmetry to the right, they have to be exactly the same. So if I took the average of my x's, then the axis of symmetry would be take the 2 plus the -1 and divide it by 2. And that's going to actually give me the exact location of where this axis of symmetry is at. It's at the spot x equals 1/2. So those are just leading into some of the things we're going to look at today. All right, so our goal is we're going to look at graphing quadratics. So we're going to get a parabola, either opening upward or downward. It's going to be a U form, and we have two different forms, intercept and vertex. At any point, feel free to pause this video, take the notes that you need. So we'll start off here with the intercept form. Graphing quadratics in the intercept form. Well, we just undid that. So if I have a form that's factored, see, here's the a value that we don't really know what it is until the equation gives it to us. And then we've got x minus p. Well, that is a factor, and x minus q is a factor. Well, where did those come from? Right? Those came from the graph. And when I set each one of these equal to 0, you don't technically need to write this, but it's just a cool way to visualize it. What if I set a or y equal to 0 and I try to solve? The a value would be divided over, so that doesn't have anything to do with it. And then I just set each factor equal to its own 0. So I'll go over p, and then I'll go over q, and then p and q are going to be 0 somewhere on this graph. I'm not sure. I just kind of these letters up are generic, so I might have a p and a q here, and exactly in the middle, wherever that might be, is the axis of symmetry. Right? So then the only thing we would need is we would need to figure out where would this vertex lie. And if I found that, then I could graph this parabola pretty quickly. So I only technically need 3 points to graph it. So let's look at what we know. If it's written in intercept form, you can quickly identify where the intercepts or where the zeros are. Where's the p and the q? Well, they're in the graph, or they're in the equation, but they're opposite of what they look like. So if this reads x minus p, remember we have to add p over. So when we say p and q are the x-intercepts, they're opposite of the way they read. So then I have p and q, and I can find the average of p and q to find the axis of symmetry. Right? The axis of symmetry is just the sum of p plus q divided by 2. And that will give me this dotted vertical line right here. And we know that our vertex lies, the x value lies on that. So if I know the x value of the vertex is whatever p plus q divided by 2 is, then all I have to do is find the y value. And if I know x, if x is a number, I can just plug it in here and here, and then I'll simplify, and whatever my output is, that will tell me the location of the vertex. Now, if the a value, if this value right here is positive, then we know our graph is going to open upward. All right. If the a value is negative, then it's going to open downward. And actually, I switched the order. I'm going to flip this really quick. Hold on. Okay, so I just had to flip this. This a value right here controls if the parabola will open up or down. If a is positive, the parabola will open upwards. If a is negative, the parabola will be opening downwards. We're not going to get into it a ton today, but you'll see this in the upcoming week. A also controls how wide or narrow the graph will be. And we'll make note of that coming up. So We know a lot about this parabola before we even graph it, just from the items that are present in the equation itself. And in this case, it is in the intercept form. So feel free and pause this video to get all of these notes down. And then we're going to go through and we'll show you how to actually graph using this notation. Okay, so here's what we got. I'm going to set this up. And again, you'll pause to get what you need. I'm just going to assume you guys will pause and take the time to write the notes. I don't want this video to be super long. So notice, if I want to find the zeros, which are also going to be the x-intercepts, you'll kind of notice those are equivalent expressions once we kind of get down to it. But how would I do that? Well, x-intercepts are always the spot whenever y is equal to 0. So if I set y equal to 0, and then I take this equation, and I algebraically solved, I would divide by 2, just like we did the other week. And then I get x minus 4 times x plus 1. It's in factored form. So now I'm going to set each one of these factors equal to its own 0. And then we'll add the 4 over to this side. And we'll subtract the 1 over to the other side. And notice x minus 4, well, the answer is the opposite of that. And then x plus 1, the answer is the opposite of that. So that's where these values come from. So I have my x-intercepts. The first thing I'll do is I'll plot those because they're going to tell me something about this graph. So go over 0, go over 4, 1, 2, 3, 4, up 0. There's my first x-intercept. And then go over 1 to the left and up 0. And there's my second. Now, you can look at the graph and say, if I'm between -1 and 4, well, what value is right in the middle of that? Well, if I go 1, 2, and 1, 2, that puts me right in the middle of those two. So I'm at 1.5. And what is that 1.5? The axis of symmetry. That's the spot where the points are equidistant from the left and the right. Now, if you don't love what I just did, you could take your two answers, and technically this is the P and this is the Q. Usually what I do, I forgot to, is write the form of intercept form. Y equals A, X minus P times X minus Q, and that way you can tell what A, P, and Q are. So the axis of symmetry was the average of your x's. So take your 4 plus -1 and divide it by 2, and we get 3/2, or 1.5. So there's the axis of symmetry. And we usually just write the equation right next to it. You can say 3/2 or 1.5, either or. But that's important because if I'm looking for the vertex, whatever value you get, notice this is x equals, I get 3/2 as my x value. Well, how do I find the y? Anytime you want to find the y, you plug it back into the original equation. So I'm going to do a little side work here. If it's easier, you could put 1.5. It's all up to you. And then I'm just going to simplify. If this is 1.5, I'll get -2.5 when I subtract. And then here I get +2.5. And then when I multiply those together, we end up with, I think it's -12, -12.5. And there's my y value. So I now know the x and y value of this vertex. Now notice, if I count, I would have to go down 12.5, but my graph only goes down by 10. So I can get creative with this, and I can call this 2, 4, 6, 8, 10. And I just might mark that as negative 10, and that tells the reader what the scale is. So you can always adjust your scale, and then that will be negative 14, negative 12, so negative 12.5. I would go over 1.5 and down 12.5, which would be about right there. So I'll label that as my vertex. Okay, and if you need to pause right now to get caught up, go ahead. We're covering a lot right now. Now, technically, that's all I need to draw this vertex, or excuse me, this parabola. I have 3 points, and if I have 3 points and one of them is the vertex, I can go ahead and draw a nice parabola. But the one thing that might be helpful is to quickly identify the y-intercept. If you can use it, it's really friendly. So what is the y-intercept? The y-intercept is whenever x is equal to 0. So what if I take this equation and I put a 0 here and here? I get 2 times negative 4, which is negative 8, times 1, which is negative 8. So the y-intercept for any form we learn is always going to be when x is equal to 0. Okay, so plug 0 in and simplify, and that just gives me one other point. Go over 0, down 8. Now actually it gives me 2 points, right? Because how far am I away here? I'm 1.5 units to the right of the axis of symmetry. So let's go 1.5 units to the left, and that gives me a second reflected point because of the line of symmetry. So now I'm going to draw my smooth U-shaped curve, and you should draw it, hopefully a straight line, continued up off of the graph, going through all the points that you labeled, and it should kind of estimate kind of the flow of the graph and the smooth curve opening upward. So let's take a look at one thing really quick. Notice the vertex is down low and the function opens up. Why does it open up? Because the a value is positive. Because the a value opens positive, the vertex has the lowest point on the graph. So that means my graph has a minimum. And that minimum value is the lowest output. So what's the lowest y value that this hits? Right there, 12.5. So I could confidently say that I have a minimum value of y equals negative 12.5. Right? So anytime we ask what the minimum is, we're looking for the y value. If we ask for where does it occur, it occurs at x equals 1.5. So there it is. That's how you graph in intercept form. I guess I kind of ignored this zeros. Notice what are the zeros? They are the solutions we had up here. It's when we set the equation equal to 0. So x equals 4 is a 0, and x equals negative 1. And the only reason why I made this comment right down here is so you could see that when we solved the work that we did last week, it does relate to this graph. And it actually makes connections to the X-intercepts. All right, so that's the intercept form, but what about vertex? How does vertex work? Vertex is a little bit trickier, but super friendly once you get the hang of it. The special thing about the vertex form is it has an H and a K, and that has movements in our graph, left and right. But notice the A value is the same A value as the intercept form and the standard form. So I just want you to make a note. Anytime you see A, it has the same effect on the graph as the other two forms. Now, we didn't really get into standard form. We're going to do that tomorrow. But that's the idea, is A does the same. If A is positive, the graph will open upward. If A is negative, then it's going to be a U opening downward. And we'll get into when it's wider or narrower in upcoming lessons. But what does the vertex do? Well, the vertex is based off of two facts. The h, notice that's in the x spot of our vertex, and then the k. So my vertex is h comma k, but what is h? Well, h is your movement left or right. Notice how it's opposite of the way it reads. This is x minus h, and we just want to take h. So h is always opposite of what you think. And I'm just going to generically move a certain distance. So let's say I move h units to the right, and then I have a plus k, so I'll just move up k units. And what does that do? That gives me the vertex. So that point on my graph is considered the vertex. And it's at the spot h comma k. Now that's really friendly because we know exactly where that vertex occurs just by reading the equation. We also know that the x value is the axis of symmetry because the vertex's x value has to go through this point. So I would not put the blue and red on my normal graph, but I would put this axis of symmetry. And that's at the equation, whatever h is, that's how far we move over. Why is that important? Because if I know one other point, then I can reflect that point over and I can get a parabola. Well, what's an easy point for us to pick? The y-intercept is, if we can use it, the y-intercept is always whenever x is equal to 0. So let's think about that. If x was 0, I would plug 0 in here, and then I would have to solve, and I would get a number. Now, we don't know what that is, but we would discover it. Now, let's just say for my example that here was my y value. Right? That's my y-intercept. So if I found that, I would count how far am I away to the left, and then I would reflect it over the same distance away from the axis of symmetry, and I'd get 2 points. And then my parabola would open upward and would go through those 2 points. And there's my parabola. Notice it's wider. From this graph that I drew, I could make a conclusion that a should be negative. I'm not going to put the negative there because this is the general form. And then also a is wider, which we haven't talked about it, but that'll be a fraction. It makes it occur slower, so it's going to open wider. So let's look at an example of graphing in the vertex form, and we'll show you how quick it could be. So here we go. And again, pause the video whenever you need to write and get caught up. But what do I have? I've got the form of a times x minus h squared plus k. You can see what each value is here. A is equal to 0.5. Notice that's positive, so I automatically know my parabola is going to be opening upward. My h value is opposite of what this reads, so I read it as x minus 3. That means h is positive 3. That's the one you have to be aware of. That negative sign is saying it's the opposite of h. And then your k is exactly what it says. This is plus k. So what I could do is I could make this a plus and that a negative, and that would tell me k would be negative 5. So where's my vertex? Well, the vertex is always at the spot hk. And we know what that is. H is 3, k is negative 5. So I'm going to go over 1, 2, 3, and down 1, 2, 3, 4, 5. And then it's always a good idea just to label it. My advice would be to label the point 2. So there's the vertex. Now, if we know the vertex, we know the axis of symmetry is always the x value. So that dotted line is going to go right through the line of y equals 3. Now, since I know the vertex, I could actually stop right here and answer this question. Is it going to be a max or min? Well, the a value is positive. My graph is going to open upward. So this vertex will be the lowest spot on the graph. So it's going to be a minimum value. And we know the minimum occurs at the y value of the vertex. We'll have a minimum value of y equals -5. Now, I will talk about the zeros in a second. Those aren't super important for this graph. What I would like to do is find one other point on this graph so I can reflect it over. And a lot of times, it's the y value that is the friendliest for us to pick. So let's let x equal 0. And I'm going to plug 0 into that equation. Notice I plugged it into the original equation. And then we're going to simplify. So -3 squared is going to be 9. It's a positive 9. That gives me 4.5 minus 5, or 0.5, negative 0.5. Okay. So my y-intercept is over 0 down 0.5, which is over 0 down 0.5. I should label that as my y-intercept. And notice it's 3 units away from the axis of symmetry. So I'm going to go 3 units to the other side, 1, 2, 3, and now I have one other point. Right? So I have 3 points and I can draw my smooth curve through there. I should mention really quick that the y-intercept isn't always guaranteed to be on your graph. Sometimes the y-intercept is so high or so low that it doesn't make sense to put on our graph. So if that's the case, you can always pick another x value. Pick another point to check. And here's a hint. What values should I pick? Well, we want easy ones, but we want ones that are close to the vertex. So if this is x equals 3, what about x equals 2? If x was 2, what is my output? So let's test that out. I'm going to plug 2 in for x, and then we'll simplify. So I get -1 squared, which is 1. 1 times 0.5 is 0.5, and I get y equals -4.5. And there is my other point. Well, let's check. If I go over 2, down 1, 2, 3, 4.5, that puts me right here. Now notice, I'm 1 unit away from the axis of symmetry. So if I reflect that point over, now I have even another point, and it's a more accurate parabola. If you really want to test, you could test 1, positive 1. And when you do that, you get a point somewhere over here, and then you could reflect that, and you just will get more and more points. Okay, oh, that's getting a little rough. But there's my smooth curve, my parabola. It's opening upward, and I have all the values that I need. Okay, so I want to make one small connection to what we did. I don't expect you to write this, but what about the zeros? What if I wanted to find zeros for this equation? Okay, well, what do? We set the equation y equal to 0, and then we solve. So I'm going to just do that down here. And again, this is something that is a definitely extra, but I think it's a helpful thing just to connect what we've already done. So if I take my equation that was given, and I set y equal to 0, and I solve, well, what do I have to do? I have to move the 5 over to the other side. So I would add 5. And then I would have to divide by 0.5, which is the same as timesing by the reciprocal, which is 2. So that would give me a 10. Then I got 10 equals quantity x minus 3 squared. So the next thing I have to do is get rid of the squared, and we'll take the square root of both sides. And when I do that, I'm left with the absolute value of x minus 3 equals 10. So then I can do some quick algebra using the idea of absolute value. That's going to give me a positive, it's going to be a negative square root 10 and a positive square root 10 as my two possible answers. So I'll set x minus 3 equal to both of those, and we're going to solve. So if I add 3 over to the other side, I get one answer. And if I add 3 over here, I get a second answer. Now, I don't love these answers, especially when graphing, so this is where I'm going to use my calculator and actually get the decimal answer rounded to 3 decimal spots. Here's the first one, and here's the second one. Okay. Now, why is that nice or friendly? Because they don't look nice or friendly at all. But what if I graphed them? X is equal to negative 1.62. Let's look at where that is on the graph. If I go over negative 1.6, that's just barely over, that's right there. Right at this spot is one of my zeros. And where's the other one? It's at 6.162, so just past 6. And I just wanted to make the connection that the algebra that we've done, all the solving that we did earlier the first week, that stuff really has value in a problem like this. You can use those skills to find the zeros. And those are just more points to make this parabola more accurate. All right, I'd like you guys to try this one. Go ahead and hit pause and work through this problem. I'm going to do it myself, and then I'll reveal the answers. Okay, so my first step is just recognizing that this is in the vertex form, A, H, and K. Notice H is the only tricky one. It's opposite of the way it reads. So x plus 4 tells me H is equal to 4. And then K is exactly what it says. So there's my vertex, negative 4, comma 8. So I'll graph that, and then I'm going to put the axis of symmetry, which, remember, the axis of symmetry is whatever H is. So I'll put my dotted line at negative 4. Okay, so I graphed my vertex over negative 4, up 8, and then I put the dotted line all the way down for the axis of symmetry at negative 4. Now, I could answer this even without graphing. Am I going to have a max or a min? Well, let's think about this. I have a negative a value, so it's going to open downward. My vertex is right up here at the top, so that is going to be a maximum value. And then what is the maximum value? Well, the maximum value is the y value, so it's the 8. So I'll have a max value of y equals 8. That's the highest output that I would ever reach. Okay, don't worry about the zeros right now, but let's find the x-intercepts. Okay, so what did I do? I took 0 and I plugged it into the original function. We simplified. So I got 4 squared is 16, negative 2 times 16 is negative 32, plus 8 gives me negative 24. Now this brings me to a very interesting position. I want to go over 0 down 24, but I already scaled my graph to go up by 1s, which means my 24 would be way, 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 way down here, and I just don't want to erase this. So in this case, this point is too large for me to plot on my graph, and that's okay. So what am I going to do? I'm just going to pick another point. And we're going to try an x value that is close to the vertex. So notice the vertex is x equals negative 4. Let's pick a number really close to that. Let's pick negative 3. And what do? We'll plug negative 3 in. You don't even need to show this work. If you can do it in your head, plug it in and we'll try. Plugging negative 3 into the original function gives me 1 squared times negative 2 plus 8, and I get 6. Much friendlier point. So let's go over negative 3, up 6, and that will give me one more point of my parabola. And notice I'm 1 unit away. As soon as I plot that point, I can reflect it over and go 1 in the other direction. Now, just for fun, I'm going to pick another value. I'm going to pick -2. And I'm just going to test another point. And actually, I'm not going to show my work on these, but I'm going to test -1 and -2 just to show you where those values would occur. So I didn't show my work, but I plugged in -2, and I end up getting 0. So I'd go over -2 up 0. Well, that's a solution. That's the X-intercept. And then if I go over 2 units to the other side, if I reflect this over, I'm going to go 2 units to the left. That gives me another 0, which those are my X-intercepts. Right here at the spot -6, 0, and -2, 0. And then if I plot the next point that I got, if I plugged in -1, simplified, I ended up getting -10. So go over -1, down 10. That's 3 units away from the axis of symmetry. I can go the other direction as well. And there's my smooth curve. Moment of truth here. We want to make this look like a U. Oh, it's not good. So do your best to make this a nice U shape. We don't want it to look like a V, if possible, because these are not linear equations. It's really hard to do this on my tablet. That should go through that point. And there you go. Okay. Now, this one was unique. I didn't have to find my zeros algebraically, but if I set this equal to 0 and subtracted 8, divided by -2, took the square root, and did all that solving, I would get the same X-intercepts and the same zeros that we got right here. All right, you don't have to write this one at all. I just want to quick go through it together and show you what we have. So the game of football starts with a kickoff, where the ball is kicked from the ground or the resting position on the ground. If the path of the kicked football can be modeled by this equation, notice the format. We've got y and x, and then we have a, h, and k, where d is the horizontal distance measured in yards, and v is the vertical distance. Using that information, we want to find what is the maximum height, how far did the ball travel to reach the maximum height, and then how far, oops, I never fixed that. Hold on. How far was the football kicked? So to answer this problem, thinking of this graphically could make this way, way faster. So let's do a very poor sketch, but what do we know? Here's A, here's H, and here's K. So I automatically know the vertex of the path of this football is opposite of what it reads. So x minus h, so h is 23, and k says go up 13.8 yards. There's h, there's k. Well, let's graph that quick. If I was to graph this, I would go over 23 yards, and then I would go up to wherever 13.8 yards would be. And you don't need a detailed graph on this, but there's my vertex. From that information, and the fact that we know the axis of symmetry occurs at 23 yards, well, we can answer the first question, what was the maximum height? What was, so they're asking for the output, the maximum height was 13.8 yards. Okay. How far did the ball travel to reach the maximum height? That is, how far on the horizontal distance. Well, how long did it take to get there? It took 23 yards, because that's the axis of symmetry, to reach its height. And I realized the one thing I didn't do is I didn't actually draw the path of the football, right, or the graph. It would go up, it would reach its height, and then it would follow the same pattern all the way down until it hit the ground right on the other side. So those are my zeros, my vertex, and my vertex is in the middle at 2318. 13.8. So then the question was, how far was the football kicked? So how far did it take to go from the ground all the way to its highest height and then land right over here? Well, that's using this idea of symmetry. I got 23 yards to get to the highest point, and if it's symmetric, it's going to reach the same distance on the other side, 23 yards. So how far did it travel total? 23 plus 23 tells me that the football was kicked 46 yards. All right, last slide. Now, we've been working with factored form and vertex form and graphing. And we started off this unit by factoring standard forms. So we took something and we turned it into a factored form, or we turned it into a vertex form. Well, how do we go the opposite way? And the key is to use our algebra friend FOIL. So let's just look at this really quick. I want to convert this function, which is in factored form, into standard form. So I needed to read ax squared plus bx plus c. What do? We FOIL. You can do this in multiple different ways. What I would do first, I believe, is the easiest, is let's distribute that 2 to the first parentheses. Okay? And then you could use FOIL here, right? First, outside, inside, last, we're multiplying. So I get 2x squared, and then I get 2x squared, 2 times 1 is 2x. Then we'll distribute the inner part, negative 8x, and then negative 8 times 1. And then you have the like terms in the middle. So those two add up to give me negative 6. And look at what I did. I took the factored form, expanded it, and now it is in the form of A, B, and C. Okay. Now we can do the same thing over here. By the way, you could use the area model for this as well. If you wanted to set up your box and just put 2x minus 8 and x plus 1. Some students like this better than the FOIL. So your option completely. So how do I deal with the vertex form? Well, the important part in vertex form is understanding what this means. What does it mean to have x minus 3 squared? Well, think about what squared means. Anytime you square something, you are multiplying it by itself. So what I'm going to do is I'm going to rethink of x minus 3 squared, and I'm going to rewrite the meaning of squared. So I'll take x minus 3 times itself. Now, you can FOIL out this blue part, right? FOIL, or do the area model. That's up to you. If I do that, I get x times x times negative 3, and then let's do the negative 3 times x, negative 3 times negative 3 is a positive 9. But notice we still have to deal with the 0.5 and the negative 0.5, minus 5. If you realize that there's spots that you can skip in terms of doing it in your head, then I'm okay with certain skips. I got to see the setup and most of the work. But now I would distribute this 0.5 to each one of these pieces inside. So 0.5 times x squared. 0.5 times negative 6 is negative 3x. And 0.5 times 9 is 4.5. And then the minus 5 finally gets dropped down. And we'll combine our like terms. There we go. Now I know A, B, and C. This is written in standard form. All right, when you are graphing, okay, we want you to use graph paper. Do not try to do this by hand. That's why you picked up graph paper at Tartan. And I want you to label the points. Notice how I labeled the vertex. I labeled the X-intercept, and I labeled the axis of symmetry. You want to label those points So the person reading your graph knows exactly what they are. All right, your homework tonight, must-have graph paper, is section 4.2. There is a PDF link in Schoology that will bring you right to this. You'll have to search. It'll say chapter 4, and then you have to go to section 4.2 and use the page numbers. But here it is. So you've got to graph the first 3 questions, and notice it's in vertex form. Use graph paper. Number 12, you just have to identify the vertex. So maybe you can do that just by looking at it. And then the next 2, 14 and 16, graph the intercept form. So you got to use graph paper. The next 3, write in standard form. So you're just doing the last 2 problems we did. You're just going to expand these out. And then on the last 2, find the minimum values. So that's just looking at what's the vertex. You don't need a graph for this. You can just kind of use the equations and go. And then the last 2 problems are similar to the football problem we just talked about. All right, good luck. Adios. Remember to submit your assignment, image of your assignment to Schoology when you're done.